We're going to talk about percent error. The objective is I can solve multi-step percent problems involving percent error. Probably where you're most likely going to run into percent error would be in science class. You do an experiment. You know the density you are supposed to come up with for aluminum is some number of grams per centimeters cubed. You come up with a different density for aluminum, and you want to know how far off your experimental value was from the actual. That'll give you a percent error, and you might have to write up about that in like a science lab. So let's talk about some vocabulary. You're going to have an actual value. In science class, it might be called the theoretical value. It's a quantity used by general agreement of the scientific community. This value does not have any error. The scientific community has come to what the actual density of aluminum is. That's the actual value. You do an experiment, you're going to have some amount of error, how much over or under a value is from what it should be. So when you do your experiment, how far above or below the actual density of aluminum did your experiment come out for the density? And then it says we'll use subtraction to use the amount of error, and this needs to be a positive, because even if you're over the amount of the actual value by a certain amount or under the actual value by a certain amount, we just want to know how far away you are from the actual value. And the percent error formula is percent error is amount of error over the actual and then times 100 to change it to a percent. So I just drew up this silly little example. Let's say the cat and dog and the babies got out of the family home and they started running down the street. And after them, suddenly this child runs, and then this child runs, and then this child runs, and then this child runs. And mom yells to dad, "Oh my God, our kids and our animals have gotten out. Let's run after them." And you see this family running past you. And you're like, wow, I'm pretty sure I just saw 9 family members run past me. Luckily, with your camera on your phone, you took a quick snapshot. The family even stopped and smiled for the snapshot before they ran along. And when you counted up how many family members actually had run past you, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there was actually 10 family members who ran past you. And we're going to figure out what's the percent error. What percent was your guess off from the actual? So your percent error would be the amount of error. Sometimes they call that absolute error, over the actual amount of family members. Then you'll multiply that by 100 to convert that decimal or fraction to a percent. So what was your amount of error? Well, your guess was 9. The actual was 10. Oh, you were only 1 away from the actual number. You could always do 10 minus 9 is 1. That's your amount of error. And that will go in the numerator. What was the actual number of family members? Well, when you took the snapshot and actually looked, you were like, oh, there's really 10. Then we'll multiply that by 100 to convert it to a percent. 1/10, 1 in the tens place, times 100 gives us 10%. Oh, you were off by 10% in your counting of this family. Not a big deal. But if you're off by 10% in terms of the amount of a chemical substance you add to something, that could be a big deal. Maybe you'd blow up the lab. Who knows? Let's go for a few more examples. Hopefully you have a calculator. It's just going to make our lives easier. Nika the dog weighs exactly 36.5 pounds. When weighed on a defective scale, oh, it's a boy, he weighed 35 pounds. What is the percent error in measurement of the defective scale to the nearest tenth? Okay, percent of error. Percent error will be your amount of error over your actual amount. And then we'll multiply that by 100 to convert it back to a percent. Well, what's the amount of error? Nika's actual weight is 36.5. The scale weighed him 35 pounds. So the amount of error, sometimes we call it absolute error, would be 36.5 minus 35, and you'll get 1.5 pounds off. That scale is 1.5 pounds off. Happens to be weighing them 1.5 pounds low, but the amount off that scale is 1.5 pounds. Over what is Nika's actual weight? Oh, we know he weighs exactly 36.5 pounds, so that's his actual. So 36.5 and then times 100. Okay, I'm going to go ahead and use a calculator to make my life easier. If you don't have a calculator at home, then you need to do that by longhand, and I just think our lives would be easier if we had a calculator. So do 1.5 divided by, put the 1.5 in your calculator first. That's 1.5 divided by 36.5. And you get a crazy decimal. The crazy decimal is 0.0410958. We're going to multiply that by 100. I can see this is going to be, that scale is about 4% off from the actual. So if we multiply that by 100, you can use your calculator or move that decimal point 2 places to the right. You get 4.1095894% as the error. Now let's just reread. Did they want us to round it? Oh yes, round it to the nearest tenth. All right, so if we're going to round to the nearest tenth, the question is this crazy number closer to 4.1 or 4.2? Well, hopefully you can see this number is really close to 4.1. We got a 0 after this. So this is about 4.1% error. That scale is going to weigh any animal that gets on it about 4.1% below what their actual weight is. All right, let's take another look at another example. It says the exact value for the density of aluminum is 2.699 grams per centimeter cubed. Working in a science lab at school, Joseph finds the density of a piece of aluminum to be 2.75 grams per centimeter cubed. Humans have measurement errors a lot of times, like we might read our graduated cylinder incorrectly, things like that. What is Joseph's percent error? Let's round to the nearest hundredth. Okay, so as soon as we know we're talking percent error, we need to find the amount of error over that actual density that the scientific community has agreed on times 100. All right, let's figure out the amount of error. So Joseph's found the volume to actually be a little bit higher than it should have been. So to find our amount of error, 2.75 minus 2.699 to find the amount of error. If you subtract and get a negative for your amount of error, that just means to take the absolute value. You want the absolute error. So 2.75 minus 2.699 is 0.051, and then we'll multiply that by 100 to, oh God, that's just our amount of error. Sorry, 0.051. That's just our amount of error, not over the actual yet. And then our actual density, the exact value of density, the scientific community has agreed is 2.699 grams per centimeter cubed. So we'll actually take our 0.051, that goes in your calculator first, divide it by 2.699. 0.051 divided by 2.699 divided by the actual. And you get this crazy decimal, 0.01889 times 100. So when you multiply that by 100, you go ahead and move that decimal point 2 places to the right. 1.8895874%. But they want us to round to the nearest hundredth. So if I want to round to the nearest hundredth, what I'm trying to decide is this number closer to 1.88 or 1.89. Well, if I look here, this 9 is like, well, that's going to bump this really close to 1.89. So this is approximately 1.89%. I don't know, in my mind, that's not really that much of an error in that the density you found to be away from the actual density, but check with Miss Bryson to see if it's a big deal in a science lab to be 1.89% off from the actual. Who knows? Sorry, let me go back to the last slide. This last problem that I'm going to go over with you is similar to a problem on your unit test. It says Sophie measured a piece of paper to be 21.7 centimeters by 28.5 centimeters. The piece of paper is actually 21.6 centimeters by 28.4 centimeters. All right, sounds good. Sometimes when we measure with our rulers, we can be a little bit off. Not a big deal, human error. It says determine the number of square centimeters in the area of the piece of paper using Sophie's measurements. So this is Sophie. So I'm just drawing out the piece of paper, and that's Sophie. Sophie believes that it's 21.7 centimeters by 28.5 centimeters. To find the area of a rectangular piece of paper, you can do length times width or base times height. So our length, we can say, is 21.7 centimeters times 28.5 centimeters. Again, I'm going to use my calculator. I'm going to do 21.7 times 28.5. You can do this longhand if you want and just double check. 618.45 centimeters squared. Area is measured in square centimeters. It's how many squares would fill up the piece of paper. All right, great. Now determine the number of square centimeters in the actual piece of paper. This is the actual, same piece of paper. Her measurements were just off. The actual piece of paper, the packaging said, was 21.6 centimeters by 28.4 centimeters. All right. Area is length times width or your base times height. 21.6 centimeters times 28.4 centimeters. Let's see what that would be. 21.6 times 28.4 is 613.44 square centimeters. Cubic would be three-dimensional. It's just how many squares fill up the figure. I don't know. So it's about 5 off. I don't know if that's a big deal or not. Determine the percent error in calculating the area expressed as a decimal to the nearest tenth. Okay. So percent error is your amount of error. Some might call it the absolute error over your actual amount times 100 to convert that decimal to a percent. Okay, so I look here. Sophie's measurement is a little bit high, and that's fine. 618. Oh God, why did I put a decimal point there? Sorry. She got 618.45 square centimeters for her area. The actual was 613.44. How far off is she? 1, 0. 8 minus 3 is 5. So she's about 5.01 off. I don't know. That doesn't seem like a crazy amount of error. So 5.01 over, you always go back to the actual. What was the actual piece of paper on the packaging? The area of the actual piece of paper was 613.44. We're going to go ahead and divide that out and then multiply by 100. So let's take a look on our calculators. 5.01 divided by 613.44 is a crazy decimal, of course. 0.0081676 times 100 to convert that to a percent. Just move that decimal point over 2 places. Oh, she had a teeny tiny error. So this is 0.81676% Round it to the nearest tenth. Is this closer to 0.8 or 0.9? 0.8. So she's only 0.8% off. That's not bad.